instructions.
Right. So then they're all like
And
actually,
we were wrong.
well, not all. You know,
We were
like a
supposed to
couple
have
fall off.
between
but
0.1 and
for the
1
most part,
percent.
just pick
It
it
was
up.
between 0.02 and 0.03.
Yeah,
And it'll like hold.
oh boy, that's. I think that's actually kind of close to what we're
Yeah, no,
Yeah,
it's actually
So
Like,
due to the instrument
yeah.
probably being completely
Never happened
broken
before.
and giving us wrong like
Everyone's
things,
familiar with the
we're just gonna
nonsense
say
thing.
systematic error and go from there.
Oh, doesn't look bad.
Yours makes a lot more sense.
Yeah.
High concentrations were coming in at, 0.0, 1.14 times e to the -4.
I'll collect it in a minute. So, there are some things that I was planning to distribute 2 months ago on the first day of the first lecture, but it's better later than never.
So basically, I'm just gonna, we all writing with instruction numbers, and we're all just saying systematic error.
We don't match sense.
Yep.
We're gonna get
You all use the
No,
same
probably
same stuff. We're good.
Think we'll get to the Zeman effect?
Probably not.
So it is a summary of the units, and as you, for the course where we were practicing mathematical stuff, it was not as important, but as we come to modeling real things, you may decide to become closer to reality with right units. The backside is a summary of basic knowledge about harmonic oscillator that you may want to memorize if you think you will ever meet it in real life. If not, you can just use it as a kindling for your fireplace. If you were taking calculus long time ago and you need a little refresher, this also needs to. My plan was to distribute it a little earlier, and there are some equations that we were using across the course. So you do recognize some simple 3 Goldman expressions and some Taylor expansions and some typical integrals, like Gaussian integrals that we were taking, right? So it is an auxiliary thing to progress in the course. And the reverse side is again a little summary about harmonic oscillator from different textbook. How people form it as exponential prefactor times Hermitian polynomials. Okay, what else I want to distribute? We are coming to most interesting, most serious, and I hope more pleasant part of the course, but our opinions may diverge. So the individual research projects are individual because you do things creatively. You do whatever you like. But if you have no idea what to do, here are some rough guidelines. Please do not be distracted by date of April 28th and the different code of the course. But it is very much related to what we will be doing for the rest of our time here. And there are no must things to do. It is only guidelines if you want. No, it's oh,
I have 3 5.
yes. Yes. I will redistribute it again. Otherwise, if you take me, there is a pile of page 1 and pile of page 2, but if I try to fix it right now, we will screw up the rest of the course. So, if you want to look on the second half, you're welcome. But let's better. I'll bring this copy again in the evening session. So I will correct my mistake, or if I'm not as humble, then mistake of my printer. I'm going to collect the homework and put a little star there to show that it was errored. Okay, but today is errored,
Oh, okay.
which means if you did it today, you will get some extra points. But if you didn't bring it today, you are free to bring it on Friday and you get just regular amount of points.
Yeah.
Which means like today it can be a little incomplete and still get full credit.
What's in there? It was at the bottom.
I got plenty of other shit to do.
So I do have a very big conflict inside myself. On one hand, I want to pretend that I care about others, and so care about you guys. Well, I'm trying to, and to make your life easier. On the other side, there is an enthusiasm and wish to complete so long program. And let me share a conflict and we will resolve it together. But I'm giving you a seed so that we find it best solution. So the presentations on research projects will be final chart of the course. It should look like very enthusiastic and positive. And I would love to avoid exam week at all, to do it at the last day of the class. But 1 hour is not sufficient. When you do things with your creativity, we need at least 2 hours. If we will find out that you guys do not have any other classes after on the last day of the class, then we can do it, avoid finals week. If not, maybe we will need to use one of the day from the finals week. No decision, I'm open for input, but I just shared my concern and conflict inside myself. Okay. So these things are very ambitious. I'm not sure if there will be enough time, but I can jam and squeeze material. That's no problem. We will come through all details through simple models, and then we will go just overview of complicated models. I think that is fine. So right today and tomorrow we will complete and we will say goodbye to harmonic oscillator. For some of you, for the rest of your career, for some of you, until next time it pops up. And the plans for the evening labs, when we will be working on the projects, are approximately sketched here. So tonight, I may cover a little bit of spin for the future, or maybe postpone it to the next time. But main goal is to design potentials. So based on your choices, I will try to be helpful in designing potentials that model your problem of choice, or showing where to take them. For those of you who have selected, and I hope to announce final wrap up of your choices, because if you did 3 choices, I need to help you to select 1 of 3. For those of you who select truly one-dimensional without different potential energy surfaces, as soon as you design potential, you can go and complete the whole project. For those of you who are so brave that you selected several potential energy surfaces, we will cover it next time on Wednesday, before Thanksgiving, if you are in the city.
So we have to do a written portion of this project.
Huh?
Correct? We have a written portion of this project, correct? Because
Wait, scroll back. repeat once again and slowly. I apologize.
So you have up there evaluation of written reports.
Oh, yes.
So is there like a rubric of like how to write these reports? Okay.
Yes. I have about 20 minutes presentation, how
Okay.
to write reports.
Okay.
I can expand it to the whole meeting or merge it together, but if you did survive unto up to this level of career, you know how to write.
Okay.
It's much less challenging than doing actual project,
Okay.
right? Well, it will take your time, but at the week where you prepare reports, of course, there will be no homeworks. It will be like replacement. High school composition on scientific subjects. Okay. So for those who are interested in several potential services, we will cover it on Wednesday before Thanksgiving. And if you are really interested but you need to travel far away for home, I'll just record and share. Last of November, we'll go on to Arrhenius plot how to, it will be general procedure. So no matter which subject you do, all data can be fit into Arrhenius plot. And you may have seen it in many courses related to chemistry. If you took chemical kinetics or exposed to part of it, you already know what it is. Connection between activation energy, temperature. It's maybe 5 minutes of basic information and 10 minutes of practical skills. And by this time, Thursday after this, it will be summary of what you have already completed. So by the evening of this, or night of this Wednesday, you have your research completed, hopefully. And then the last Wednesday before last Friday, you may just, reports will be hopefully done, but in preparation for verbal oral presentations, you may review how to visualize your findings in a better way, so that you include movies in your presentations. But it is kind of extra thing on the top of the actual research. Okay. So and I will do an effort to pay all my dues in form of homeworks next Friday. It is my goal. What is it? Oh, it is a homework that you have brought, right? Good. Here are your choices, and I'm trying to work through them and cross out things that I do not like and highlight those that I like, and keep only one subject per person. But it is premature to share, so it's just my teaching. Many thanks for voting. So 2 lectures ago, we agreed that. Oh, what are we doing? We are completing harmonic oscillator, which is a model of anything vibrating, like in the interatomic distances, infrared spectra. And right now, we are looking not only the regular infrared spectra, which are useful to identify molecules, but kind of last century. Right now we are looking on femtosecond chemistry, or we are building basement to look on the femtochemistry, photochemistry. One short laser pulse excites system from ground to excited, and then it vibrates in a way similar to classical oscillations. But these vibrations near the equilibrium may result into coming close to the barrier and overcome reaction barrier from the harmonic potential to something different, to dissociation or charge transfer to different reaction. So without this, for some of you, boring step with regular harmonic oscillator, it's very hard to go to unharmonic and exciting stereochemistry. So we are doing the coherent state, which is an analog of oscillating oscillator, right? Classical oscillations. So how do intuitive oscillations project onto the quantum background that we have already developed? So we decided to use the concept of annihilation operator and explore eigenstates of annihilation operator, which means finding that can be done in two ways. One, looking for expansion coefficients over the basis, or a good basis, which is a good basis of eigenstates of harmonic oscillator, which we were doing last Friday, Monday. And second way is to go back into our favorite coordinate space. So for expansion coefficients, for the expansion in the basis, we did identify that there are recursion relations between expansion coefficients of lower and higher order that did allow us to find it. And we found that such state, which is quasi-classical, in the limit of very low vibrational frequency, very high mass of vibration, this equation will be transferred into classical vibrations of just point charges. Okay? But if it is a classical particles or classical objects, quantum objects, they have distribution, they have width, and they can be expanded in the basis of eigenstates of oscillators with these coefficients. Independent of whether it oscillates with high or low amplitude, where it starts, the functional form is always the same, and everything is parameterized by one parameter, which is initial elongation and phase factor that accumulates. If you ever need to calculate by pen and paper without any computer, any observable related to harmonic oscillator, and most of the tasks for theoretical chemistries, computing observables that would agree with experiment, hopefully. You just take this expansion coefficient, this wave function which is known in the basis, and make a sandwich with operator of your observer. So although right now you are doing like a sports lady from a couple of Olympics ago, like not impressed, but this is a powerful thing. It almost, the designer of this equation was like a tiny hair from getting a Nobel Prize. So it's really important and healthy. And now we are departing from this thing and going back to Cartesian space. So if we will be late for any completion, then here is what we are going to do. And you may have guessed it, or if I will browse through your homework, I may see that you anticipate this sort of answer. So the initial state, which is a Gaussian distribution but elongated from equilibrium, will start moving forth and back with a frequency corresponding to oscillator. And main thing that you have completed, those who have already completed, was that there is a magic width parameter. If you take the width too large or too small, it will start oscillating. But if you find something in between, it will move forth and back without changing the width. So if you guess this width correctly, then it will be Gaussian distribution with fixed width, fixed uncertainty of position, but the center of the Gaussian distribution will harmonically browse forth and back, right? And in the limit of classical theory, it will correspond just for negligible width, this very sharp width. And in classical, in quantum, it means that the width is formulated in terms of frequency, mass, and Planck constant. Questions? Objections? So you're basically done. And now there will be a little of boring technical details, which you may or may not need ever in your life. I just fulfill my duties of delivering it. And if you have looked through the handout that I distributed on Monday, you may have seen it from the British scientists, right? I'll draw this map later again. We went through three-particle box, three-dimensional box oscillator, and then we need rotation, spin, and other things. And here are 10 evolution, time-dependent, time-independent Schrodinger equation, Heisenberg equation of motion, these two states, ladder operators, and coherent states, right? And intersections of the model and method is what we covered in the course. 20 seconds. Empty. What does it mean? Okay. So our belief is that acting by annihilation operator on the coherent state, which we already discussed the answer, we will get this coherent state again. This is the protocol. This is a trick that we have practiced to find the ground state of oscillator. The ground state of oscillator is a coherent state of zero displacement. So if you put, instead of mu, if you put 0, it will be an equation to find the ground state. A comment. It will not make us more wealthy, but it may help to establish connections inside the brain. In fact, what I'm doing now is senseless. We do not need it. As soon as we know functional form of the eigenstates of the oscillator, okay, which are one sombrero, a camel with 2 humps, a camel with 3 humps, and we know expansion coefficients from the coherent state, the C0, C1, C2. We just multiply eigenfunction by expansion coefficient and build the resulting quantum state. We will be completely correct, legitimate, and nothing else is needed. The thing that I'm doing now is just few steps shorter. So philosophically, it is not useful, not needed. It's just less mathematical effort. Because adding together complicated functions is not always fun. Well, this thing may be not fun for you as well, but it is a little bit more easy. So, what we are going to do? We are going to express annihilation operator as position and momentum with appropriate coefficients. And by plugging it into here, we will get a differential equation, which will have one term more compared to what we did 2 weeks ago. So before we had only 2 terms, x times psi, ddx times psi equals 0. Now we will have one more term. So it will be just a little bit more complicated. And then we will solve it, multiply onto itself with complex conjugation, and get the probability distribution that we have already looked at. So, I was not lying. I was just not optimal in choosing letters for variables. So what we used to call mu, a textbook suggests that we will use letter gamma. And I want to correspond to the book if you are looking at it. And then I have a luxury of using this textbook as a cheat sheet. So under gamma, now we understand the time-depending eigenvalue of annihilation operator that keeps the same, it should be gamma naught, the same absolute value, but accumulates phase and rotates in complex plane. If I do not write anything, just go through slide, then we can be really quick. You're not taking notes, I'm not writing anything, so you'll be a companion on the quick road. So this is the definition. I've forgotten to give you a quiz about memorizing this equation. It's a big loss. So it's Angela, can you please help and move the screen to the lower left? Thank you. So you can guess that here will be x, here will be p. So it's linear superposition of position and momentum with some coefficients. So coefficients in front of the position is mass and frequency, and in front of momentum is just imaginary unit. And then outside, it is the square root of this stuff, which is, as you will see in the next line, will be related to the width parameter. So what I can do here, at least you see from the handwriting that I was not just copying equations from the textbook, which is also possible as a next level of simplification. So we can pull the factor from upfront back inside the brackets, then cancel similar terms, and then one identifies a symmetric arrangement. Well, we already went through it a couple of weeks ago. So the factor in front of x is mass time frequency over Planck constant, and factor in front of derivative is inverse of that, Planck constant over mass and frequency. So we can identify this thing as the width parameter and just keep calling it this way. So width times derivative, 1 over width times position. Good. And now it is time to practice linear differential equations. Should I? 2 c x c d dx. And here I put psi equals gamma psi. How do we solve this equation? You know, there are a lot of standardized protocols how to solve differential equations if they are complicated, of high order, with non-homogeneous, but here it is yet a simple thing that can be done by a single integration. So we can place everything that is related to free variable on one side and everything that is related to the function on the other side. And then we integrate both sides. Right? So this is d psi dx. What if we multiply left and right part by dx? No one forbids us to do so. So dx will pop up here, it will disappear here, and it will pop up here. What if we divide, symbolically we divide each term by the unknown function? Then the function will disappear here, disappear here. No, it will stay here because it is deep side, and disappear here. 1, 2, sigma dx, x dx. Right? Catch me if you can. It's not hard. I'm doing many mistakes. Plus sigma stays here, d psi stays there, and dx is gone. Right? Gamma. Here we got psi because we were dividing it by. And here we get gamma multiplied by what? Yes, thank you. So if our goal is to split free variable and function onto different sides, then we can take this part and move it to there, right? Then on the left we will have the something that is easy to integrate and is related only to the function, and on the right we will have things that depend only on the free variable. Okay, I'm even a little ahead of myself. So minus 1 over 2 sigma x dx is just gamma dx yes. Should there be sigma somewhere in this term? No. But we can bring it here by dividing everything by sigma, right? So remove it here, put here sigma square, here sigma, gamma by sigma. So what is the integration of the 1 over function?
Natural log.
Anyone wants to object? Check.
I agree.
It doesn't show this integral, so I need to memorize it. But yes, it is natural log. And here we integrate linear function and the constant. Right? So we have logarithm of psi, maybe divided by some normalization constant. Equals to, what is the integral of x dx? You just do not want to help me. Right? And what is integral of dx? Right? So what is interesting that the square term comes with minus and the linear is positive. When we did the same exercise 2 weeks ago, we didn't have this gamma term. And then this would give the Gaussian function centered at 0. What is the next step? If it would be your homework rather than mine.
Exponentiate both sides.
Yes. So exponential to the power of left and right side. Then on the left you have psi divided by c sub 0, and on the right it will be exponential minus all this stuff. 1 over 4 x squared over sigma squared plus gamma x over sigma. And we can remove coefficient here and put it there. So we do have the wave function, which is eigenfunction of annihilation operator. It is in Cartesian space. It doesn't coincide with, unless it is gamma equals 0, it doesn't coincide with any of eigenstates of Hamiltonian, which means it will not stay the same with time. It will perform some dynamics. And this dynamics is hidden in the value of gamma, which is time dependent. To some sense, we are done. But the gamma is complex number, and plotting complex functions is not always pleasant, as you have seen on last presentations. There will be real part, imaginary part. And if you need just to assess the motion of the center of the packet, why don't you look on the probability distribution, which is wave function absolute value squared, right? So again, a little conformistic step to follow the notations of the book. So by some reason, this British scientists decide to treat separately constant phase, that is phase that has been set up at initial time, and a phase that has been accumulated with time. So this gamma naught is absolute value that corresponds to elongation, and then there is a time independent phase and phase that accumulates with time. And also all phase together can be equal with letter theta. So this is done to just process complex conjugation in the easier way. So when we are going to practice the probability distribution, which is wave function conjugated times wave function, we will need to conjugate everything, including the gamma parameter. And we may prepare this step ahead of time, telling that if you put a little star in front of the gamma naught is unchanged, and for the phase, we just swap the sign in front of this imaginary component. Psi times psi star. So both of them do have they have same functional form of Gaussian exponentials, or we will bring them to Gaussian form. But it has the quadratic form that is the same for conjugated and non-conjugated, and we do have the difference here and there in the star symbol in on the top of gamma, right? So when we multiply two exponentials, it means we can add together their powers. So if we add together powers of the quadratic terms, they will just yield factor 2 in front. But the complex eigenvalue of integration operator cannot be just added, or cannot be multiplied by 2. They're different, so we need to keep them as gamma plus gamma star. Right? All true. Gamma plus gamma star. Something like this. And again, why do we torture ourselves by this exercise? Because we want nice distribution, and we already saw in the answer that everything will be real, no complex numbers. So here there is something complex, but we expect that it will stop being complex. Who helps us to avoid imaginary exponentials and complex numbers? Right after explaining two things. Old body Euler. So if gamma is gamma naught times e to the power I theta, then gamma star is same as minus exponential, and these two this combination can be replaced by a cosine theta, where theta is constant in initial phase plus accumulated phase. Right? So in our expression for probability distribution, we will replace the summation of gamma and gamma star by gamma naught times cosine of theta, of the phase. So basically we are almost done. So this is initial phase, and I may screw up the sign, but plus or minus it will be the same result. So initial phase, accumulated phase, cosine, initial elongation, x. So a little step to make it looking more pleasant. So we want to bring it to the Gaussian shape, which means exponential of something squared. So this top line can be brought, we can identify the full square there. If you look on this x squared over sigma squared as a squared, this is a, this is factor 2. So we can identify this one as b, and then bring it into the form of a minus b squared, right? For this purpose, we need to add and subtract whatever we defined as b. Objections? No. So then the thing that we constructed is a plus b, a minus b, will come to the power of exponential here. Here is our b squared, which is our price to making this trick, but we may remove it and assume that wave function square probability distribution should be normalized. We just take this function, normalize it, and get all normalization in this prefactor. And it is sometimes it is much quicker than to follow this time-dependent oscillating factor. So then we can call this combination of absolute value of annihilation eigenvalue times position as center of the wave packet, right? And then we construct it in the form of Gaussian distribution, where center is time dependent. So same, it's like a mouse hidden by somewhere and starts walking forward and backward. So center of distribution is moving forwards and backwards. In your homeworks, you got this result plus something more valuable that will be a big effort to do by pen and paper. You also found some regimes where the width is time dependent. I will not answer. Well, many thanks for investing your time, for coming, listening, and for planning to complete inspiring individual research projects. Meeting is over. I will stay here to answer questions. Thank you.
Two.
Yep.
No, but I was able to get it. Yes. So no effort is needed.
I gotta see if I got them.
Curious, because I really thought
Oh, actually.
yeah, because there's two problems. One problem, the last problem, the hard one, I didn't have